Hi, this is a supplementary Algebra 2 lesson for lesson 64.B in your workbooks, complex numbers. I'll be working on page 263 and 264 in your workbooks, the examples there. So if you want to grab them and go ahead and pause the video, do that now. So just real quick, what is a complex number? The book mentions a complex number is any combination of real numbers and imaginary numbers. Okay, and remember we have this Euler's notation, the I, excuse me, to denote the imaginary part. So when we combine a real number and an imaginary number in any way, we get a complex number. And that review for that Euler's notation, so I stands for the square root of -1. I squared, therefore, will equal -1. Okay, and then just a quick review of the rules of radicals involving negatives under the square root symbol. If we have two numbers multiplied together, two square rooted numbers, I should say, two radicals multiplied together, one of them is positive and the other is negative, okay, we can multiply them both and put that negative under the square root symbol, just like we do multiplying if the radicals are both positive. Okay, you just simply multiply the numbers and put it under the square root symbol. But remember, if both of them are negative, there's the new rule. We cannot multiply minus a times minus b, because that would result in a positive ab. We have a new rule for that. If both of the numbers under the square root symbol are negative, we put the negative outside, okay, and then multiply them. So remember, there's two separate rules depending on how many negative radicals are involved. Okay, let's go over the first example, 63.4. At the bottom of page 263, they say to simplify a square root of 2 times the square root of minus 3. Square root of minus 2 times the square root of minus 3. Okay, so the drill is we're going to get rid of that negative symbol, okay, by replacing it with an I. So the square root of 2 remains, and the square root of 3 remains, okay, and we get I. Okay, so now we have two positive numbers underneath the radicals. We can multiply those as normal according to this rule up here. Okay, it becomes the square root of 6, and then we can multiply the i's together. I squared. I times I is I squared. Okay, I squared is another expression for -1, so we're going to replace that. So we get a -1 square root of 6 as the answer. Now notice, when we've multiplied the two negative radicals together, just like our rule states over here, what is the result going to be? It's going to be a minus on the outside times the numbers multiplied together. And that's what we come up with here. Okay, so in the case of this, if we see this, we can kind of take a shortcut method. Instead of going through these 4 steps, we can go to this rule and say two radicals, minus radicals, negative radicals multiplied together, it's simply the minus of those two multiplied, like that. So that's the shortcut step using this rule. Okay, it's the same thing when we go down through the Euler's notation. Okay. Going to the next example, simplify this expression, 4i to the third minus 2i to the fourth plus 2 square root of 9, square root of -9, plus minus square root of -3 times square root of -3. Okay, so we have a mixture of Euler notation and radical symbols, so we're going to combine it all into the Euler notation, okay? And again, what they said from previous lessons, when we have multiples of I, we're going to list them all out, all three of those I to the third, and then group them in groups of 2. Here we have a 2, and we have 4 of those I's together, and we're going to have 2 groups of 2. Okay? And here, instead of going through the Euler notation like it does in the book, and you can certainly do it that way, we just saw from the previous example, we can go to our rules here and take that shortcut. Okay? So, what we have here, well, we don't have 2 radicals multiplied together, but what we can do, okay, is take an I out of this expression, okay? It would result, in other words, this would result in square root of 9 times I. I'm just going to do that mentally, okay? I can take the square root of 9, it's 3. 3 times 6, or times 2 is 6. Okay, I can't multiply the 9 and the 2. Remember, I have to take the square root of 9 and multiply it to the 2. And then I have my I. Okay, so I'm kind of doing 2 steps in one there. I hope that doesn't confuse you, but that's what I've done here. And then on this next expression, we do have a case where we can go over here and use this shortcut method. Okay, instead of going through the Euler notation and combining them, just like we did in the last example, I'm going to do the shortcut. I'm going to move that minus sign to the outside and then multiply the numbers together, okay, would be 9. Okay, and of course, if I do the double step, the 2 steps in one, that would become this. It would simply become 3 because the square root of 9 is 3. But if it changes into from a positive to a negative 3. Okay, so then the drill is for every pair of i's, I squared, I'm going to say that's the equivalent of minus 1, minus 1, minus 1. Go ahead and put the minus 1 above your parentheses if that helps you keep track of things. Okay, and so then what do I have? I have a 4 times a minus 1 times an I. I have a minus 4 I. Over here I have a minus 2 times a minus 1 is 2 times a minus 1 is a minus 2. I don't have any i's left over. I still have a 6i. I still have a minus 3. Then I combine my i's together. Okay, I have a 2i. I have a minus 5. Now, it's more appropriate to express it with the real number first, or minus 5 plus 2i. That's the preferred method. You put the number first, even if it's a negative, and the imaginary part second. Okay? So go ahead and turn your pages over to example 64.6. On the next page. So one of the handy methods of this Euler notation is it gets rid of our radical symbols, and then we can perform regular mathematical operations. The real numbers with the real numbers, the imaginary numbers expressed as I with the imaginary numbers. We can kind of keep them separate and yet do the mathematical functions we normally do, which are much more complicated if we have the square root, the radical symbols involved. And here's an example of that. On 64.6, they're having us multiply 2 complex numbers. There's our first complex number, a combination of real and imaginary numbers. And here's our second complex number. Okay, and because they're both in Euler notation, like I said, we can perform the regular mathematical functions on that, like the distributive property. Let's go ahead and do that. Okay, a 5i times 4 is a 20i. We can multiply the number times the number, and I times, well, it doesn't have anything to multiply by, so I remains. Okay, we have a 5i times 3i, that becomes 15i squared. Okay, let's do the distributive here. A minus 2 times a 4 is a minus 8. A minus 2 times a 3i is a minus 6i. And then we just combine the terms together. Okay, so we get a 14i, or excuse me, let's do it in descending order. We have a 15i squared. We have a 14i. We have a minus 8. And again, we're going to, if we have groupings of I and I, or I squared together, we're going to replace that with minus 1. Okay, so 15 times minus 1 becomes minus 15. The i's are gone then. We're left with a 14i and a minus 8. Let's combine it with the real numbers up front, a minus 23, and the imaginary number in the rear, a minus 14i. Okay, and that is our solution there. So Euler notation is very convenient for doing mathematical operations, normal mathematical operations, which would be a lot harder and much more confusing if we had all of those square root symbols involved. So we just got to remember, we apply the operations, the numbers to the numbers, the imaginary parts, the i's to the i's. Okay, they're kind of separate entities. Okay, but we can apply our rules of I up here to simplify it in the end. So I hope that helps. Shoot an email or a text message with any questions. So long for now.